Alright, so in our opening video for 3.1, we are going to be solving systems of linear equations. The first thing that we're going to be doing is solving systems with tables and solving systems with graphs. And then in the next video, we're going to move on to some of our other methods like substitution and elimination. So starting with graphically, or this first one is going to be numerically by using a table. So we've used tables to graph equations before. This time we're going to use a table to set up some different values and then figure out exactly where the two intersect. Because remember, this represents a line that you could plot, this represents a line that you could plot, and so what we're looking for, our solution, is the point where the graphs intersect. So I actually want you guys to write that down. When we say that we are looking for the solution of a system of equations, what that solution is the point where the lines intersect each other. So most of the time, but not all the time, there's going to be one point where the two lines would cross. And we'll talk later about different situations that could arise where it's not one point exactly. Okay, so we're going to set up a table for both of these. Before we set up a table, so if you are solving using a table, what you want to do is get it into slope-intercept form. Okay, so that's going to be our first step. Okay, so we want to get into y equals mx plus b if you are solving using a table. Okay, so we're going to start with this one, this top one. All you have to do to get into y equals mx plus b is subtract the x from both sides. So we have y equals, and I'm going to put the negative x first just so it's in the right order, plus 3. And then the second one, I'm going to add 2x to both sides to get the y by itself. Okay, so I have y equals 2x minus 6. Okay, so what I'm going to do is I'm going to set up a table for the two of them. So a good table, so we'll start with the line y equals negative x plus 3. I'm going to make a table for this one. So a good place to start would be to use these values. And I know it seems like a lot, but it's pretty quick and easy because these are simple equations that you could just plug the value in. So then I plug in negative 3. Negative x means I make it opposite. So positive 3 plus 3 would be 6. Make this opposite. So positive 2 plus 3 would be 5. Positive 1 plus 3 is 4. And then you'll start to catch a pattern. So see this? There's technically a negative 1 in front of the x, so that means that every time x goes up 1, y goes down 1. So once you catch that pattern, you can just fill the table in like that. Okay, so now let's make a pattern for our second graph. Y equals 2x minus 6. So I'm going to use the same values. I'm going to start by plugging them in, and then I'm going to look for a pattern. And what we're hoping is that we'll find a common point that they both have, because that'll be where they intersect. And if we don't, then we'll have to add to these table. So plug in negative 3 times 2 is negative 6. Minus 6 would be negative 12. Okay, first multiply this by 2 and we get negative 4. Minus 6 is negative 10. Negative 1 times 2 is negative 2. Minus 6 is negative 8. Okay, so the pattern here is that every time x goes up 1, y is going up 2. That's my slope. So all I have to do is add 2, add 2, add 2, add 2. All right, so let's take a look. Here's just kind of our starting values for the table. If I don't find a match, I'm going to have to add some more. But so if we look through, we're looking for a point that matches. Oh, and luckily we found one right at the very end there. Okay, so our solution would be the point 3, 0. If we hadn't found one, we would have to keep adding points, and you could add like negative 4, negative 5, or you could add 4, 5. Keep adding points until we find one. Now, you'll notice this is not the most convenient method. It could take a while. So let's move on to another method, and this is solving by graphing. Okay, so when we are in, this is standard form, you actually just want to leave it in standard form. It's super, super easy. So say you are in standard form. You want to plot using x and y intercepts. That's the easiest way to plot if you are in standard form. So we're going to plot using x-intercepts and y-intercepts. So start with this first one. So for my x-intercepts, remember for the x-intercept, what you do is you plug in 0 for x. So for your x-intercept, you set y equal to 0. So if I plug in 0 for y, this term will just be gone, and then I just have x equals 0. Okay, and then if I plug in 0 for x, that's how I find my y-intercept. If I plug in 0 for x, I can divide both sides by -2, and I just get 0 for y. Okay, so all I have right now is 1 point, and I can't connect the dots if I only have 1 point, so I will have to plug in one more. So maybe we plug in 2. Let's plug in x equals 2. Okay, so plug in 2 for x minus 2y equals 0. So I can subtract 2. The only reason I'm doing this is because my x-intercept and my y-intercept turned out to be the same value, so I only have 1 point so far. Okay, so I end up with y equals 1. Okay, so now I have another point, the point 2, 1. So I can go over to 2 and up to 1, and I can plot that. Okay, so now I need to be super, super careful and detailed when I'm plotting this. Notice this pattern is I went up 1 and over 2. So I'm going to go up 1 over 2, do it again. So be super, super careful when you're plotting. Okay, so you can also go down into the left 2, down into the left 2, down into the left 2. So you have to be very, very, very detailed if we're trying to solve by graphing, because we need to know exactly where they intersect. Okay, so now go to the second line. Now we're going to do x plus y equals 6. Okay, so start with my x-intercepts. Remember, to find my x-intercept, I set y equal to 0. So that means I could just cover up this y. It's like I'm setting it equal to 0. And so I get 6 for my x-intercepts. And for my y-intercept, I plug in 0 for x. So again, it's like I'm just covering it up if I'm plugging in a 0. So I get 6 for my y-intercepts. Okay, so x-intercepts, I can go 1, 2, 3, 4, 5, 6. That's my x-intercept. And for my y-intercept, I can go up 1, 2, 3, 4, 5, 6. Okay, and then just connect the dots. And I've got to be super, super careful when I do. That I'm connecting them perfectly so that I can figure out exactly where my intersection point is. Okay, so we found it, and if I wasn't being super detailed, we may not have found exactly where that point is. Okay, so that is our intersection point, and if we count from the origin, that is the point 1, 2, 3, 4. That's the x value. Okay, so 1, 2, 3, 4, and up 1, 2. Okay, so our intersection point is the point 4, 2. It's a solution to both of those equations. Okay, so just really quickly, we're going to talk about some definitions here: consistent, inconsistent, independent, and dependent. Okay, so a system is consistent if it has at least one solution. Okay, so if a system has at least one solution, it is consistent. And then the opposite is true for inconsistent. That means it has no solutions. Okay, a solution is independent if it has exactly one solution. Okay, so for example, this last one is independent because it has exactly one solution. And then an infinite number of solutions would be dependent. And you will see examples where that happens. Okay, so our third example here, graph each system and describe them. So we are going to set up these graphs. So we're going to graph by using x-intercepts and y-intercepts. So for this first one, our x-intercepts, so if I plug in 0 for y, I would divide both sides by 6. So my x-intercept would be 15 over 6, which I can reduce down by 3, and I get 5 halves, which is 2.5. So I can plot right at 2.5 there. And then my y-intercept for this second one, I plug in 0 for x and divide by -4. So I get 15 over -4, which doesn't reduce down, but we can put it into a mixed fraction. So I can tell you it is -3 3/4. So we can go down -1, 2, 3, and 3/4. Just do your best guess there. Okay, so connect the dots there. That's my first line. Let's do the same thing for the second. So my x-intercepts, I plug in 0 for y, and then I can solve for x. So if I divide both sides by -6, I would have 18 over -6, which is -3. So I can go -1, 2, 3. That's my x-intercepts. And then my y-intercepts, plug in 0 for x. So divide both sides by 4. And I can reduce this down to 9/2, which is 4.5. So up 1, 2, 3, 4.5. Okay, so I can connect those dots. Okay, looks like that. So these lines are actually parallel to each other. So if we look at the definitions, it is not consistent because it'll never have a solution. Parallel lines will never intersect each other. So it is inconsistent. It has no solutions. Okay, so this system is just inconsistent. And then since it has no solutions, it wouldn't fit with either of these definitions either. Okay, so it's just inconsistent. These ones, okay, I can go ahead and plot this. Okay, my x-intercepts, I plug in 0 for y, and I can divide both sides by -4. So I have -17 over -4, which reduces to 4 1/4. Okay, so I'll plot that right there. My y-intercept for the second one, plug in 0 for x, divide both sides by 5, and I can reduce this down to -3 2/5. So just do your best estimate there, and then connect the dots. Okay, for the second one, x-intercept for the second one, plug in 0 for y, and you can divide both sides by -4. So 15 over -4. And that is, we have the same thing right here. So that is -3 3/4. Right about there. You're just estimating. And then the y-intercepts, plug in 0 for x, divide both sides by -2. So -15/2, which is -7.5. So down 3, 6, 7 will be a little below that. Okay, so then go ahead and connect the dots there. Okay, so you can see they would cross in exactly one place there. So I do have at least one solution, and more specifically, I have exactly one solution. So this is an independent, consistent system. Okay, so to kind of sum up the 3 different scenarios that we could have, draw a little picture. So we just saw 2 different examples. We saw an example where the lines were parallel, and when lines are parallel, they will never cross each other. And so this is an inconsistent system. If you have parallel lines, there will be no solution that's common to both of them. We just saw a separate scenario where you had one line like this, one line like this. They would have one intersection point. And so that is a consistent and independent system. Okay, and then I have a third scenario where what actually happens is you've got a line like this, and then when you graph the other line, it actually ends up being completely identical to the first line. So it's like one line right on top of the other. And so what would happen is it's intersecting each other in literally every possible point. So it'd be an infinite number of solutions. So that would be consistent and dependent. So if they turn out to be the exact same line, that means they have an infinite number of intersection points, which would make them dependent. All right, so that's it.